Hi, welcome back to the lecture series on abstract major theory with course code MTH701 and MMTC201. Today in this lecture we will discuss the differentiability of monotone functions. Differentiability of monotone functions. First of all, we define upper derivative and lower derivative. For a real valued function f, for a real valued function f, with domain D to R, D the subset of R, we define the upper derivative for a real valued function f with domain D and x and xb be the interior point, be an interior point, x be an interior point, x be an interior point of D, the domain of the function. So interior means we can find an open interval with center x, and that open interval is contained in D. The upper derivative of f, we define the upper derivative. The upper derivative of f at x, which is denoted by d upper f of x, okay, d dash f of x, and the lower derivative of f and the lower derivative of f at x, which we denote by d lower dash, it is f of x, okay, are defined as follows, are defined as follows. Upper derivative of f at x is defined by its limit h approaches to 0, then we take the supremum 0 less than mod of t less or equal to h f of x plus t minus f of x divided by t, and its lower derivative is defined by, and the lower derivative of f at x is equal to limit h approach to 0, infimum 0 less than mod of t less or equal to h f of x plus t minus f of x divided by t, So these are the definitions of lower derivative and upper derivative. So name it 1 and this one is second. Now look at the supremum. Now what is the supremum actually? The supremum 0 less than mod of t less or equal to h f of x plus t minus f of x divided by t. This supremum, it is an increasing function of h. Okay, it's a function of h actually when t is varying from 0 to h, or actually this t is less or equal to h and greater or equal to minus h. H is a positive number. So this is same as the supremum of minus h less or equal to t less or equal to h, where this h is a positive number. T is also a positive number. T is not a positive number. H is a positive number. F of x plus t minus f of x over t. So this is it is the supremum of the ratio f of x plus t minus f of x divided by t, where t varies over minus h to plus h. It's obviously an increasing function of t. You can see this is an increasing function of h, not t, function of h, where this h is a positive number. This is an increasing function of h. So therefore, when as h is approaching to 0, this limit will be actually infimum, because it increases with h, but whenever h is approaching to 0, the limit h approaches 0 will be equal to the infimum of this supremum. So therefore its limit h approach to 0, supremum 0 less than mod of t less or equal to h, f of x plus t minus f of x divided by t is actually the infimum, where infimum runs over h is positive number, and supremum 0 less than mod of t, this supremum runs over t less or equal to h, f of x plus t minus f of x divided by t. Similarly, from second, the limit h approach to 0, infimum of 0 less than mod of t less or equal to h, f of x plus t minus f of x divided by t. This infimum will be a decreasing function of t. Therefore, whenever limit h is approaching to 0, this will be actually the supremum. It's equal to the supremum h positive, infimum 0 less than mod of t less or equal to h, f of x plus t minus f of x divided by t. So first limit is actually the infimum of the supremums, and second limit is actually the supremum of infimum. Okay. Now you can easily verify that the function is differentiable if its upper derivative is equal to lower derivative. Now one can easily verify that this upper derivative is always greater or equal to lower derivative. That's very simple. One can easily verify that upper derivative of f at x is less or equal to the lower derivative of f at x. Okay. So this upper derivative is less or equal to lower derivative, and f is differentiable, at x if both the derivatives are equal. If upper derivative of f at x is equal to the lower derivative of f at x, and the common value is denoted by is denoted by f dash x. So you verify this upper derivative is less or equal to lower derivative, and you also verify that if the function is differentiable, then if upper derivative is equal to lower derivative, then f is differentiable and its common value will be equal to f dash x. That's the standard notation for the derivative. It's f dash x. That function is differentiable and the derivative is denoted by f dash x. So, you have seen that the mean value theorem in your BSc course. So let me state that theorem again here. The mean value theorem tells us that the mean value theorem tells us that if f is continuous, on the closed interval AB and differentiable on open interval AB, then there exists a point C belongs to the open interval AB such that f dash C is equal to f of B, such that f dash C is equal to f of B minus f of A divided by B minus A, or you can write it as B minus A times f dash C is equal to f of B minus f of A divided by, not divided by, it is f of, so name it third. Now if this derivative is greater or equal to some particular number alpha, if f dash x is greater or equal to alpha on this open interval A comma B, then third gives what's third? Third is this is greater or equal to f of alpha. Then third gives this alpha times B minus A, which is this alpha is it's f dash is greater or equal to, this alpha is it's less or equal to, alpha is less or equal to f dash C because it's on AB less or equal to C. C is a point of this interval, so it's less or equal to this times B minus A, and this one is equal to f of B minus f of A. That's, we can say this, that is alpha times B minus A is less or equal to f of B minus f of A. So this is our mean value theorem. Okay, this way alpha times B minus A is less or equal to f of B minus f of A, where this alpha is less or equal to f dash x on A minus B, or f dash x is greater or equal to alpha. Now we extend this theorem to monotone functions. Okay, so what's its extension in measure theory? So let me state this lemma as lemma. So you can see this here. This B minus A is actually the Libig measure of the interval on which the function is defined. Actually, it's Libig measure of that set. Actually, so here B minus A will replace this by Libig measure. Okay. Let f be an increasing function. Let f be an increasing function. Let f be an increasing function on closed and bounded interval AB, on closed and bounded interval AB, on closed and bounded interval AB, then for each alpha, then for each alpha positive with the measure, with this Libig measure of the set of the points x belongs to the upper interval AB, where this upper derivative is greater or equal to alpha, is less or equal to 1 by alpha times f of b minus f of a, f of b minus f of a. So it's actually the generalization of this result, because we can write this as b minus a is less or equal to 1 by alpha f of b minus f of a, and on this upper interval the derivative is greater or equal to alpha. Okay, the measure of the set where the derivative is greater or equal to alpha is less or equal to 1 by alpha times f of b minus f of a, because here the Lebesgue measure of the set on which the derivative is greater or equal to alpha is b minus c, because that's the whole interval AB. So that's why it's here b minus c. B minus c is the Libig measure of this set where the derivative is greater or equal to alpha. Now look at here this one. It's the Libig measure of the set where the upper derivative is greater or equal to alpha is less or equal to 1 by alpha times f of b minus f of e. So it's some sort of generalization of this mean value theorem. Okay, yeah. And not only this, and the Lebesgue measure of the set where the upper derivative is infinity is 0, and the Lebesgue measure of the set x belongs to AB where this upper derivative is infinity, the Lebesgue measure of this set is equal to 0. Okay, let's prove this theorem. Proof. So our alpha is a positive number. It's given in the statement also. So let's take this alpha positive, and let's define the set. For this alpha positive, we define a set. Define E alpha is equal to those points of the interval AB where this upper derivative is greater or equal to alpha, where this upper derivative is greater or equal to alpha. And let's choose any point alpha dash in the interval 0 to alpha. So that is this 0 less than alpha dash less than alpha. Okay, so therefore upper derivative of f at x is it's greater or equal to alpha, but alpha is greater than alpha dash. Okay. Now this also means, what's this upper derivative? It's actually the infimum of the supremums. Okay, it's actually, so this means the infimum, it's a positive number, and the supremum f of x plus t minus f of x divided by t, minus here, minus f of x divided by t is this supremum is taken over 0 less than mod of t less or equal to h. It's t here, mod of t less or equal to h. This is greater than alpha dash. So this infimum is actually infimum over h is greater than alpha dash. So this means the supremum 0 less than mod of t less or equal to h f of x plus t minus f of x divided by t is greater than alpha dash for each h positive, because you are taking infimum with respect to h, and this infimum is greater than alpha dash. Therefore each member of the set where you are taking the infimum the set infimum of the set, okay, so infimum of the set, this infimum of this set, the set of the supremums whenever you varying this t over h, okay, is greater than alpha dash. That means each member of the set must be greater than alpha dash. So that means this is greater than alpha dash for each h positive, okay, this is greater than alpha dash for each h positive. This is h here. Okay, name it fourth. Now we take the collection of closed intervals and we'll see that that collection is a Vitali cover of E alpha. Let F be the collection of closed and bounded intervals CD, collection of these type of intervals satisfying the following property, for which those closed intervals for which f of d minus f of c is greater or equal to alpha dash times d minus c. We will show that this collection is a Vitali cover of E alpha. We will show that F is a Vitali cover of this F is a Vitali cover of E alpha, okay, E alpha, it's a Vitali cover of E alpha, okay. This we will see. So for this we choose any point. Let epsilon be any positive number and x belongs to this E alpha, and we need to find the one of the closed interval in F such that x belongs to that closed interval and the Lebesgue measure of that interval is less than epsilon, okay. From third, because third is true for each h positive, therefore this is true for epsilon by 2 also. From third we have this alpha dash is less than supremum of 0 less than mod of t less or equal to epsilon by 2 f of x plus t minus f of x divided by t. Now there exists from this expression, from this inequality, we can conclude that there exists some t naught. There exists some t naught. with 0 less than mod of t naught and less or equal to epsilon by 2, such that this f of x plus t naught minus f of x divided by t naught is greater or equal to alpha dash. We will see this is true. There is some t naught with this property. Now if not, then for all t with 0 less than mod of t, this less or equal to say epsilon by 2, where epsilon by 2 is any positive number. Instead of h we have chosen epsilon by 2, such that this reverse inclusion holds. So that is f of x plus t minus f of x divided by t is reverse means is less than alpha, which means the supremum is less or equal to alpha, less than alpha dash. Sorry, it's alpha dash here. It's alpha dashes. For this means the supremum 0 less than mod of t less or equal to epsilon by 2 f of x plus t minus f of x divided by t is less or equal to alpha dash. A contradiction, a contradiction to which a contradiction to this, let me name it fourth, because alpha dash is less than the supremum, and here I will get alpha dash greater or equal to fourth. So thus there is some t naught. So thus there exists t naught. Thus there exists t naught with 0 less than mod of t naught less or equal to epsilon by 2, okay, is less or equal to epsilon by 2, such that this holds, such that f of x naught plus t minus f of x divided by t naught, such that f of x naught, such that f of x naught plus t minus f of x naught divided by t is greater or equal to alpha dash. Is greater or equal to alpha dash. Is greater or equal to alpha dash. This is here. Sorry, it's not x. It's t naught, not x naught. Okay, I wrote x naught. Okay, this is x here, not x naught, but this it's t naught here. Okay, which implies that f of x naught plus, sorry, it's not x naught, f of x plus t naught minus f of x is greater or equal to alpha dash. So on this interval, so if t naught is positive number, t naught is either positive or negative, t naught is positive, greater or equal to this, for a positive, because it's true for each t, I will assume that t naught is positive. Okay, by choosing t naught a positive number, because it's true for each mod of t naught less or equal to epsilon by 2. So I choose t naught a positive number lying in this interval with this property. In fact, I can choose t naught is equal to epsilon by 2. So I can choose t naught is equal to epsilon by 2 as well. I can choose t is equal to epsilon by 2 as well. Okay, epsilon by 2, this is here. By choosing T naught is equal to epsilon by 2. So thus we have an interval, we have a closed interval, thus there exists a closed interval x to x plus epsilon by 2 such that this x belongs to the interval and Lebesgue measure of the interval is it's equal to epsilon by 2, that's less than epsilon, and one more thing, it's satisfying this property, f of x plus epsilon by 2 minus f of x is greater or equal to alpha dash times the length of the interval b minus a, it's epsilon by 2. Okay, so it's in f, that is this interval x to x plus epsilon by 2 belongs to f, and x is in there. So hence this f is Vitali cover actually. Hence f is f. So for each epsilon falls to and for each x in E alpha, we can find an interval in our collection f such that x belongs to that interval and the Lebesgue measure of the interval is less than epsilon. So thus f is a Vitali cover. Thus this f is a Vitali cover of E alpha, and by the definition of Vitali cover we can find a finite digit collection in this class. Now by Vitali covering lemma, by Vitali covering lemma, there is a finite digit collection. There is a finite digit collection. See these intervals ck, dk with 1 lesser equal to k lesser equal to n. There is a finite digit collection of f. For which this Libig measure of E alpha minus that union of these finite digit collections ck, dk, k runs from 1 to n is less than epsilon. So this is from Vitali cover. Okay, name it phi. Now this E alpha we can it's a subset of E alpha minus that union. K runs from 1 to n ck dk, then it's union with that collection. Union k runs from 1 to n So first I am removing this union from E alpha, then I am again adding. Okay, so it's always subset of this, because this union contains some elements which may not be in this E alpha. So therefore that's why it's contained in this. Okay, in case this E alpha is subset of the union, then obviously the equality holds. Obviously, okay, and there is no harm to write the equality. But in general, it's subset of this. It's subset of this. So this implies what's the Libig measure of E alpha now? Libig measure of E alpha. So you can write that the disjoint actually here it's Libig measure of this set plus Libig measure of this but this is not a measurable set, so I can apply sub-additive property of Libig outer measure. It's less or equal to Libig measure of union Ck dk, k runs from 1 to n, plus Libig measure of E minus union k runs from 1 to n Ck dk. Okay, this apply here again sub-additive property. It's less or equal to summation k runs from 1 to n, or you can apply additive property because they are disjoint now, so you can write equality here, but this one is less than epsilon, so I can write strictly less actually. So this is equal to this actually, but this one is strictly less than epsilon. That's why I have written here it is strictly less than summation k runs from 1 to n Libig measure of these intervals. That's obviously dk minus ck. So first I will write it here, plus epsilon. Okay, but this is summation k runs from 1 to n Libig measure of ck dk is dk minus ck plus epsilon. Now what's this dk minus ck? It's because this collection is in f, and on f we have a following property of f. What's that property that I want to see here? F is a collection of intervals satisfying the property, this one, alpha dash times d minus c is less or equal to f of d minus f of c, or d minus c is less or equal to 1 by alpha dash times f of d minus f of c. So d minus c, so that means dk minus ck is less or equal to it's here actually, this line, you can see this line, if whenever this interval CD belongs to the collection F, then it's satisfying this inequality dk minus d minus c is less or equal to 1 by alpha dash times f of d minus f of c. So for the interval ck dk, it will be dk minus ck less or equal to 1 by alpha dash times f of dk minus f of ck. Okay, so it's less or equal to 1 by alpha dash times this. So this is equal to summation, this dk minus ck will be less or equal to 1 by alpha dash times f of dk minus f of ck. So that's in the next page now. It's again less or equal to 1 by alpha dash times summation k runs from 1 to n. This dk minus ck is less or equal to 1 by alpha dash times f of dk minus f of ck. Okay, f of dk minus f of ck plus epsilon. But since function is monotonic increasing, therefore they are all positive distances, and they are also disjoint intervals, and function is monotonic increasing. These intervals are also disjoint. So it's actually that this f of d1 minus f of c1 plus f of d2 minus f of c2, this length cannot be greater than f of b minus f of a, because function is monotonic increasing on this interval ab. On this interval our function is monotonic increasing, therefore this sum cannot be greater than f of b minus f of a, as the intervals are disjoint. So this is less or equal to 1 by alpha dash times f of b minus f of a plus epsilon, because as f is increasing, and this collection ck dk for 1 less or equal to k less or equal to n is disjoint, is disjoint. So thus we have this, it is less or equal to less than 1 by alpha dash times this plus epsilon. So thus Libig measure of E alpha is less or equal to less than thus Thus Lebesgue measure of E alpha is less than 1 by alpha dash times f of b minus f of a plus epsilon, and this is true for each epsilon positive and each alpha dash belongs to the upper interval 0 to alpha. 0 to alpha. So letting this alpha dash approaching to alpha and epsilon approaching to 0, this will be Lebesgue measure of E alpha will be then less or equal to, this is true for all alpha dash belongs to the open interval 0 to alpha and epsilon positive. So letting epsilon approaching to 0 and alpha dash approaching to alpha, we get, so this gives Lebesgue measure of E alpha is less or equal to 1 by alpha times f of b minus f of a. So that proves the result completely. So the first part of the theorem is complete now. Now we prove the second part of the theorem, where we had to show that the Lebesgue measure of the set where this upper derivative is equal to infinity is 0. So for this, for each natural number n, for each natural number n, for each natural number n, we have this set x belongs to the open interval a b such that its upper derivative is equal to infinity, it is a subset of En, because on En means the upper derivative is greater or equal to n. So whenever x belongs to this, that means upper derivative is infinity, that means upper derivative is always greater or equal to n. So that means x belongs to En, because by definition of En it means that the upper derivative is greater or equal to n. Okay, so whenever upper derivative is equal to infinity, it is always greater than n. Okay, so it is always subset of En. But the Lebesgue measure of this set is less or equal to this. Okay, so Lebesgue measure of this set is less or equal to Lebesgue measure of this, and the Lebesgue measure of En is less or equal to 1 by n. Name it 5. From 5, this means Lebesgue measure of the set x such that this upper derivative is equal to infinity is less or equal to Lebesgue measure of En, and from 5 it's less or equal to 1 by n times f of b minus f of a by 5 by, and this is true for each n, letting n approaching to infinity, we get Lebesgue measure of the set x such that its upper derivative is equal to infinity is equal to 0. It cannot be less than 0, it is equal to 0. So this proves the theorem completely. Now next we prove Lebesgue's theorem, which is very important, and next theorem is the Lebesgue's theorem. Okay, Lebesgue's theorem. Lebesgue's theorem. If function is monotone, so if the function f is monotone, if the function f is monotone, on the open interval AB, on the open interval AB, then it's differentiable almost everywhere, then it is differentiable almost everywhere on AB. Means it is differentiable on AB except on a set of measure 0, or you can say that except on a set where the upper derivative is strictly greater than the lower derivative. Okay, because upper derivative is either greater than lower derivative or it's equal. In general, upper derivative is greater or equal to lower derivative. So whenever upper derivative is equal to lower derivative, that means function is differentiable, and whenever function is not differentiable, it means that the upper derivative is strictly greater than the lower derivative. So we need to find the set where this upper derivative is greater than lower derivative, and we will see that the Libig measure of that set is actually 0. That will give this function is always differentiable almost everywhere. So here in our proof we assume that f is monotonic increasing. We assume that assume f is monotonic increasing, and this interval is bounded open interval. Assume f is monotonic increasing, and this interval AB is bounded, is a bounded open interval. Suppose it is a bounded. Now next we'll see that for what will happen when this interval is not bounded. Okay, is bounded open interval. Okay, now we show that the Lebesgue measure of the set X belongs to AB such that its upper derivative is greater than the lower derivative is equal to 0. We show that this set is a null set actually. So how do we do that? How do we do that? First we verify that first we verify that the set first we verify that the set X belongs to AB such that upper derivative is greater than lower derivative is the union of the sets is the union of sets, or you can say I will write it as is the union of sets is the union of these sets X belongs to AB such that let us denote this set by say it's equal to say F. This F will show that this F is the union of these sets upper derivative greater than alpha, greater than beta, greater than lower derivative, where these alpha and beta are, and denote these sets by E alpha beta. Okay, where alpha comma beta are rational numbers, are rationals. Okay, now this is easy to verify. That is we show that this F is actually union of E alpha beta. In fact, it's double union. Okay, union over alpha and union over beta. F is union of these E alpha betas. So this is a very simple. Let's choose X in F. Let X belongs to F, which means that the upper derivative of f at x is greater than the lower derivative of f at x, and we can find rational numbers between these two. Let alpha and beta, because they are real numbers, are rationals such that this upper derivative of f at x is greater than alpha and alpha is greater than beta, which is greater than lower derivative of f at x. So which means that x belongs to E alpha beta. So that means x belongs to union of E alpha beta. All such union E alpha beta, where union runs over alpha and beta. Now conversely, assume that x belongs to this union. Conversely, assume that x belongs to double union E alpha beta, that x is in some one of the E alpha beta, then there exists alpha beta in Q, say alpha less than beta or alpha greater than beta. Alpha may be less than beta or greater than beta. We assume that alpha is greater than beta, such that x belongs to E alpha beta, which implies that the upper derivative of f at x is greater than alpha, greater than beta, and greater than lower derivative. You can also choose this beta less than alpha. X belongs to, there is alpha and beta, say such that x belongs to E beta alpha. Then in that case you can write this x belongs to E beta alpha, where the upper derivative is greater than beta, greater than alpha, and greater than lower derivative. So this gives this upper derivative is strictly greater than the lower derivative. So which means that x belongs to f. So thus this f is actually the union. Thus this f, it's actually union of E alpha beta, where alpha and beta runs over rational numbers, where alpha and beta are rationals. Since the rationals are countable, so therefore this collection E alpha beta, such that alpha beta belongs to Q, is a countable collection, is a countable collection. So thus therefore in order to prove that Lebesgue measure of f is 0, we need to show that Lebesgue measure of f is 0. Therefore in order to prove that Lebesgue measure of f is equal to 0, it is sufficient to show that Lebesgue measure of each E alpha beta is 0. Then you can apply the Lebesgue measure of f is less or equal to the double summation Lebesgue measure of E alpha beta. Now if Lebesgue measure of each E alpha beta is 0, so this is the countable sum of zeros, which is equal to 0. Okay. So thus in order to show that Lebesgue measure of it is sufficient to show that it is sufficient to show that Lebesgue measure of E alpha beta is equal to 0 for all alpha beta belongs to Q. So let's denote this E alpha beta by E. So we show that Lebesgue measure of E is equal to 0, and we show that this Lebesgue measure of E is equal to 0. Lebesgue measure of E is equal to 0. Now we choose an open set O. Choose an open set O for which this is very simple. You apply this the definition of outer Lebesgue measure. Okay, E is subset of O, subset of A, B and this Libig measure of O is less than Libig, so it's strictly less than Libig measure of E plus epsilon, name it it's expression 1 in our theorem, this. So this is strictly less here, not less or equal to. Okay, so choose an open set O such that E subset of O covers C and O is obviously subset of AB. So if it is not subset, we take the intersection of O and AB. That will be an open set again containing E, but that open set will be subset of AB, such that Libig measure of O is less than Libig measure of E plus epsilon. Okay, so this can be done. It's from the definition of the Libig outer measure of E. You can easily find it. This is not difficult. Now let's take the collection of closed interval. Let F be the collection of B, be the collection of let F be the collection of closed bounded intervals, closed bounded intervals CD, closed bounded intervals CD, closed bounded intervals CD contained in O, for which this holds f of D minus f of C less than, not greater but less than D minus C. Now here what's this beta actually here? This beta has the following property. It's E alpha beta. Okay, what's this beta here? Beta has the property that this one, you can see it here. Beta has the property that its upper derivative is greater than alpha, but its lower derivative is less than beta. So we apply this lower derivative formula. Lower derivative is greater than, less than beta, and we will see that this collection is actually the Vitali cover. It's a Vitali cover of E. Okay, since as in the previous theorem, since where we use the upper derivative, here we use the lower derivative. Since this lower derivative is less than beta, so in that case, in our previous theorem, the upper derivative was greater than alpha, and in that case we have chosen the intervals CD such that f of D minus f of C is greater than alpha times D minus C, and in that case the upper derivative was greater than alpha. But here we choose the reverse. Actually we choose the interval CD such that f of D minus f of C less than beta times D minus C, and since this lower derivative is less than beta, therefore it's a Vitali cover up. Therefore, as on similar lines, on E, this F is a Vitali cover of E. So it follows on similar. It follows on similar lines as in the proof of previous theorem, as in the proof of previous lemma. That was the lemma actually. As in the proof of previous lemma, this F is a Vitali cover of E. Okay, so this F is a Vitali cover of E. So for let epsilon be any positive number now, let epsilon be any positive number. Let epsilon be any positive number. So by Vitali covering lemma, by Vitali covering lemma, there is a finite disjoint collection. There is a finite disjoint. There is a finite disjoint sub collection. Say Ck dk, where this k runs from 1 to n in F. So this collection is in F, for which this holds Libig measure of the set E minus union Ck dk, k runs from 1 to n is less than epsilon. This is the second expression. Okay. Now by definition of this collection, because they are in F and F has some property, by definition of this Ck dk, we have this closed interval Ck dk, we have summation k runs from 1 to n f of dk minus f of Ck. Now look at the definition of this these intervals. Actually, you can see here. What's the definition of these intervals? F is a collection of intervals C D such that f of d minus f of c is less than beta times d minus c. And these Ck dk, they also belong to F. They also belong to F. So f of dk minus f of ck is less than beta times dk minus ck. So this is less than. This is less than beta times summation k runs from 1 to n dk minus, and they are digit intervals, and they are also subsets of, each interval is subset of O. So you can see this is equal to beta times the Libig measure of the union of ck dk's, Libig measure of union ck dk. It's closed interval ck dk, k runs from 1 to n, because they are disjoint intervals. So Libig measure of these intervals is equal to summation of the sum of the Libig measure of the intervals, and the Libig measure of the intervals is equal to dk minus ck. So this equality holds because these intervals, these ck dk's, they are actually disjoint intervals. You can apply the additive property of Libig measure. But each ck dk is subset of O, so union is also subset of O. This is less or equal to beta times Libig measure of O, because these ck dk, they are subset of O for all k runs from 1 to n, 1 less or equal to k, less or equal to n. So it's less or equal to Libig measure of beta times Libig measure of O. But what's Libig measure of O? It's less than Libig measure of E plus epsilon. Here you can see it where it's here. Libig measure of O is strictly less than Libig measure of E plus epsilon. So this one, this is now less than. So this is now less than Libig measure of E plus epsilon. This Libig measure of O. So thus we have. So this gives this implies the summation k runs from 1 to n f of dk minus f of ck is less than beta times Libig measure of O, but Libig measure of O is less than Libig measure of E plus epsilon. Okay, name it third. Now we apply the previous lemma. Okay. Now we apply the previous lemma when we restricted our f to ck dk. That lemma was proved for the interval ab, but we apply that lemma when f is restricted to the interval ck dk. Now for 1 less or equal to k less or equal to n, we apply the previous lemma when f is restricted on this interval ck dk. On the interval ck dk, then what is this f of dk ck from the previous lemma? What's that previous lemma actually? So let me write that interval for the interval for this for the open interval ab in general. That lemma states that this Libig measure of the set X belongs to open interval ab such that its upper derivative is greater or equal to alpha. This Libig measure of this set is it's less or equal to 1 by alpha. 1 by alpha times f of b minus f of a. Now you apply the same thing to the interval ck dk, and here it will be less or equal to 1 by alpha times f of dk minus f of ck. So you apply this thing, this lemma. This is the lemma actually that you have proved. Okay, you apply this lemma to our theorem in our theorem here. So we get this Libig measure of E, but restricted to the interval ck dk actually, to the interval ck dk. E means that the lower derivative, the upper derivative is greater or equal to alpha. Okay, because E is a set E alpha beta where the upper derivative is greater or equal to alpha, but restricted to this interval actually. This one, it's actually this here. So this means that the f is restricted to the interval ck dk, and also here E means that upper derivative is greater or equal to alpha. So this one is less or equal to 1 over alpha times f of dk minus f of ck. This is less or equal to this. So therefore from second we get second gives Libig measure of E. Libig measure of E is obviously less or equal to Libig measure of you can write it as Libig measure of E intersection ck dk plus so this is less or equal to, actually you have to apply the additive property here. Okay, Libig measure of E, you can see this is equal to, this is less or equal to, you can see this is less or equal to Libig measure of the union ck dk. K runs from 1 to n plus Libig measure of this E minus union ck dk. K runs from 1 to n. Okay, this is less or equal because E is subset of this union union E minus union. Okay, it's as in done in the previous theorem. Same thing. Now this will be less or equal to Libig measure E intersection this. Okay, this is less or equal to Lebesgue measure of or you can apply the equality here also, or you can write this as strictly less here, because this is strictly less than this is strictly less than this is strictly less than. Here you can apply the summation summation k runs from 1 to n Lebesgue measure of ck dk plus epsilon, because that one is strictly less than epsilon. It is a strictly less. It is strictly less than epsilon here. Now this one, it's again less or equal to summation k runs from 1 to n Lebesgue measure of E intersection these closed intervals ck we have to apply it on those intervals actually. So how do we do that? It's E intersection, then E intersection this it's E intersection ck dk plus complement. Okay, so I will write it as this is not the correct way to write it. Okay, so let me see the previous page first. Here this is not correct. This is not correct. Now from second we have Lebesgue measure of E. Let me see it like this. Lebesgue measure of E is equal to Lebesgue measure of E intersection. Let me write it as this: union ck dk k runs from 1 to infinity, then again union, then again union. You write union k runs from 1 to n ck dk, its complement here. Okay, let's write this is the complement of the union here. Okay, so it's E intersection union, and the union, the complement of this union. This is actually the whole space now, and this E intersection whole space is equal to E. Okay, and this is equal to Lebesgue measure of the E intersection the first union, union k runs from 1 to n ck dk. Okay, then it's a union E intersection the second union, which is actually the complement, union k runs from 1 to n. You apply that distributive law of intersection over union is so you can see this is like this. Okay, now it's okay. So it's E intersection union. Okay, then union E intersection union. So this union is set actually. It's write this as A. This will be A complement. It's A union A complement. So it will be E intersection A union E intersection A complement. So now it's simple. Now apply the subadditive property. It's less or equal to Lebesgue measure of the first set. Lebesgue measure of E intersection union k runs from 1 to n ck dk. Okay, plus Lebesgue measure of the second set. It's E intersection the complement. It is equal to E minus that union. So A intersection B complement means A minus B. Okay, k runs from 1 to n ck dk. Now this can be written as this is equal to Lebesgue measure of. Now you can write it as union k runs from 1 to n E intersection these ck dk. okay, plus this set. This is as it is a Libig measure of E minus union k runs from 1 to n ck dk. Here you apply second. What second? Second means Libig measure of E minus this set is less than epsilon. You can see the second here. That's why I have write it as therefore from second. Second gives. Second means this one. Where is second expression? Where you have written this is less than epsilon. E minus that finite union is less than epsilon. This is second. Okay. Now you apply here second. Okay. This is plus this. It's second. And here you apply this one. What's the previous page? Here you apply that sub-additive property. Libig measure of union is less or equal to summation of the Libig measures, and here you apply the second property. So this is less or equal to summation k runs from 1 to n Libig measure of E intersection ck dk plus epsilon. This is by sub-additive and second property. Okay. So now this one, it's by third. This is less or equal to where you have applied the previous lemma. I have to name that statement here. You have applied the previous lemma somewhere. This one. So name it here fourth. Okay. Name it this fourth, not fourth. It's maybe fifth. So fifth. This is fifth. Okay. So you apply fifth. Libig measure of E intersection ck dk is less or equal to 1 by alpha times f of dk minus ck. So this is now less than, or you can say this is less or equal to 1 by alpha times summation k runs from 1 to n f of dk minus f of ck plus epsilon. Again the function is monotonic increasing and they are disjoint intervals. This sum is less than f of b minus f of a. This is less or equal to 1 by alpha times f of b minus f of a plus epsilon. So don't think to write it f of dk minus ck plus epsilon. So name this expression. This has 6. That one. This is less or equal to 1 by alpha times summation summation k runs from 1 to n f of dk minus f of ck plus epsilon. Now from these two, from 4 and 6, okay, from 4 and 6, from that last expression, this 4 and 6, we get this Libig measure of E. Libig measure of E is less or equal to beta of alpha. This you verify. It is very simple. You have to plus 1 by alpha times epsilon, plus 1 by alpha times epsilon plus epsilon. Okay. This you. Where is the expression 4? I want to see that. This is 6 and this is 5. So I think this is third actually. You have to apply third, not this third. 4 is nowhere. 4 is not there. So you apply third and 6 here. Third and 6. Okay. You apply third and 6, not 4 and 6. Okay. This is third and 6. Apply third and 6, you will see this Libig measure of E is less or equal to beta by alpha times Libig measure of E plus 1 over alpha times epsilon plus epsilon. And this is true for all epsilon a positive number. So this means the Lebesgue measure of E must be equal to 0, because if it's not equal to 0, letting epsilon approaching to 0, this means Lebesgue measure of E is equal to 0. Otherwise, what will happen? Letting epsilon approach to 0, we will get Lebesgue measure of E will be less or equal to beta by alpha times Lebesgue measure of E by letting epsilon approach to 0. These will go because it's not equal to 0. Otherwise, this minus Lebesgue measure of E, Lebesgue measure of E is not equal to 0. Then they will cancel out this Lebesgue measure of E and Lebesgue measure of E. We will get alpha is less or equal to beta, which is a contradiction. A contradiction, as alpha is greater than beta. A contradiction, as alpha is greater than beta. So thus we have this Lebesgue measure of E is equal to 0. That is what we have to we need to show actually this one. Lebesgue measure of E is equal to 0. So this is done. So that means every monotone function is differentiable almost everywhere. From this we have a small exercise. Show that a function of bounded variation, is differentiable almost everywhere. So this is actually simple. So suppose a solution. Let f be a bounded variation. Let f be a bounded variation, then f is equal to g minus h, where g and h are increasing, where g and h are increasing, and hence differentiable almost everywhere, by Lebesgue's theorem that we had done by Lebesgue's theorem. So g and h are differentiable almost everywhere, therefore f is differentiable almost everywhere. Therefore f is differentiable almost everywhere. So that means every function which is a bounded variation is differentiable almost everywhere. So that completes this lecture. So in the next lecture we had to define the divided difference function and average value function.